Swayam Prabha. Digital India. Educated India.
We have been discussing about the imperfection crystalline solids. Last time we were primarily concentrating on the point defects, that is the defects which is restricted to a particular lattice site, and for example, there may be vacancies, there may be interstitials or some foreign atoms substituting the original metallic ions or oxygen ions and so on. So, those are called 0 dimensional defects. There are also other variety of defects, either they may be 1 dimensional, 2 dimensional and at times 3 dimensional as well. So, today's topic is 1 dimensional defect, and that is called also dislocations. So, our topic today is dislocation. While point defects which we have discussed last time primarily affects the properties of solids or properties of materials such as electrical properties, optical properties and also mass transport properties like diffusion and so on. Dislocations are more important to investigate or to understand the mechanical properties or mechanical behavior of the crystalline solids. Now, they were primarily discussed or researched on in the area of metals and alloys, where there is a considerable amount of plastic deformation. We will try to understand what is plastic deformation. However, in ceramics their importance is relatively less, but even then as ceramics being a part of material science, there is always a comparison with other kind of materials, and therefore, it is necessary or even for the ceramics to understand what is dislocations and how it is important for the mechanical deformation of crystalline solids. To start with, I like to compare the stress strain diagram, which is one of the very key features of the mechanical behavior of all solids, of 3 different groups of materials. One is of course the ceramics, the other is the metal, and the third one is plastic, and they have a distinctly different mechanical behavior. To start with plastic, as you can see, what we have plotted here is basically strain. Strain means the deformation, the extent of deformation, and then against a mechanical stress. So, when you apply a mechanical stress, any material there is a deformation, and deformation means there is a change in the atomic dimensions, not the atomic dimension, the interatomic distance, and of course, it depends on the nature of the bond and nature of the interatomic forces. So, in plastic being a very soft material, it can be extended at a very low pressure or a low stress, mechanical stress over a long distance. That means, a very large strain can be produced with small amount of mechanical stress, whereas metals is in between, and it needs larger stress to attain the same amount of strain, whereas ceramics, which is known to be a brittle material, it needs much larger stress even for a small amount of strain. Now, the strain in any material is there are 2 kinds of strain. One is what we call the elastic strain, the straight line portion of the curve is elastic strain. If you strain or if you apply the stress up to this point, then there is a reversal. That means, it springs back to its original size as soon as the stress is released or stress is removed. Same case, the same situation happens in case of metal salvage. This is up to this point, it is a what we call a elastic behavior. That means, as long as the stress is there, you have a deformation, and if the stress is released or removed, there it comes back to its original size or shape. So, this is what we call a elastic deformation or elastic range, and in this the stress is proportional to strain. Stress is directly proportional to strain, and that is the basic rule of or law of Young's Hooke's law. So, Hooke's law applies when there is a elastic strain, and the ratio of the stress to strain is the Young's modulus. So, that is the simple concept of Young's modulus for any material. And if you are comparing the ceramic material, as you can see from this diagram, you need a much larger stress to attain a very small strain. And of course, the Hooke's law applies almost up to the end of this curve. So, there is the elastic range is very large, whereas beyond that, beyond this elastic range or what you call the yield stress, particularly for metals, this part of the diagram, or either in case of metals or in case of plastic, it is called the plastic deformation. That is an irreversible kind of deformation. So, if the stress is beyond the elastic limit, then there is a irreversible deformation or permanent deformation, and even if you remove the stress, that permanent deformation is retained. Only a small fraction of the deformation gets released, or comes a small portion of deformation is recovered, and that is the elastic part. So, any deformation of the material consists of two parts. One is the elastic deformation and there is a plastic deformation. And the characteristics of ceramics is that the elastic parts, elastic stress or elastic component is much larger, and it needs a very high stress to generate a small strain, and therefore, as the stress strain ratio is the Young's modulus, the Young's modulus of ceramics in general are much higher, much larger than even for metals, but the plastic deformation is almost very negligible. So, it breaks. This downwards line is basically actually the breaking line or breaking points. So, after certain deformation, plastic deformation, very small amount of plastic deformation, almost negligible plastic deformation, ceramics breaks, whereas metal takes a lot of plastic deformation or a permanent deformation before it breaks. And if plastic, of course, most of the time it takes a lot of strain even at a lower stress, and sometimes it breaks and sometimes it comes back a rubbery kind of material. So, our point of concern here is the plastic deformation range, how this plastic deformation takes place, because there is a breakage of bonds, and or the bond length may be increase, and then it is a permanent increase, it does not come back even if you remove the stress. So, we understand there is some phenomena which is taking place at the structural level, at the atomistic level. So, let us try to understand what actually happens at the atomistic level when there is a plastic deformation, a considerable amount of plastic deformation. Well, before that, let us try to understand, can we make a theoretical calculation of how much stress, external stress is needed to make a or generate a strain. Strain is nothing but a movement of atoms, movement of relative movements of the different layers of the atoms. Okay. So, in the atomistic level, we can visualize in this manner. If this is two different layers of the atoms, both are in the closed packed position, this is first layer and this is the second layer. So, we apply a shear stress. The lower end we apply a stress in this direction, and the upper end on the upper side we are applying a stress on this direction. So, it is a kind of not normal stress, it is a shear stress. So, we are trying to slide down, slide the upper layer of the atoms over the lower layer of atoms, bottom layer of atoms. And the distance here, these are the some kind of interatomic spacings. On this side is A and this side is B. So, once it is trying to deform, you are applying stress. So, this atom will try to move to the next atom, and this will go to the next atom, and so on. So, this is the deformed position. This is the arrangement when one interatomic spacing has been moved on the first layer, or the top layer has moved by one interatomic spacings. Now, during this movement, one thing has happened, because this is not a, since it is a spherical surface, that is the consideration, that is a fair amount of assumption so far as the atoms are concerned, the size of the or shape of the atoms are concerned. So, there is a hill over which the atom has to move. So, initially it is sitting on a trough, here it is sitting on a trough, and then when you are trying to move to the next trough, then there it is going through a hill. Okay. So, there is it has to move up and then come to the next trough. So, initially there will be a increasing stress, you need more and more stress as you go up the hill. When you coming to the down the hill, then of course, you need less stress. So, you do not need an uniform stress to make a deformation in that crystal or relative movement of the two layers. You do not need always an uniform stress. Initially you need a increasing stress, and then the stress comes down as it goes over the hill. Okay. So, as the top point is reached, the maximum of the stress is reached, and then you need less amount of stress to remove for further movement. So, as a result, you can plot the stress, variation of stress as a function of the distance, interatomic spacing. So, that is plotted in the next picture, in the next slide. This is basically a sinusoidal curve. So, on this side it is vertical axis is stress and the horizontal axis is displacement. So, this is your B, total distance is B, interatomic spacings. So, you have the maximum stress is needed here, and then it goes down, and then again on the other side you need a lower stress. So, it is a negative stress actually. So, actually you follow this kind of a wavy pattern of stress. It is not an uniform stress is needed for the movement. So, it basically one can assume a sinusoidal variation this and as a function of displacement. So, one can calculate what is the maximum stress needed for this relative displacement. In fact, although we can idealize situation is a sinusoidal curve like this, but in real sense this varies like this, according to the dotted line. But we will, as for our calculation, we will assume that it is as a sinusoidal variation. So, if that is the case, one can really find out what is the maximum stress, shear stress needed for this displacement or this deformation. Assuming a sinusoidal variation, the shear stress versus displacement curve may be written in this fashion: tau equal to tau max, that is the maximum stress needed, sine of 2 pi x by b. x is the distance at any point of at any stage or the total displacement at any stage. The small values of displacement, because we are talking about very small values, Hooke's law can be applied, and the stress, or one can write tau is equal to g, d is the shear modulus of the material we are considering, and x by b is the strain. So, it is the shear stress into shear strain. So, tau is this, the stress equal to shear modulus into the strain, and if we apply that to this equation, then tau becomes tau max 2 pi x, once again it is an approximation. So, 2 pi x by b, and then from that one can find tau max equal to g by 2 pi b by a, and if x is almost equal to a, then tau max becomes g by 2 pi. So, if we know the shear modulus, then you can also find out what is the maximum shear stress needed for the deformation to take place, and that is a fairly simple calculation, and of course, the approximate calculation, it is not a very accurate calculation. It is just kind of an order of magnitude calculation. So, shear modulus of metals are in the range of about 100 GPa, and if you use that value, the tau max is of the order of 20 GPa. It comes to about that value. However, the experimental value, this is a kind of theoretical value from the structure point of view, from the atomic structure point of view. Okay. However, if you experimentally try to find out what is the value of tau max, or what is the shear stress needed for the deformation, maximum shear stress needed for the deformation, we find it is much less. Okay. It is about 1/100th of what is expected of a theoretical value, and that was quite disturbing for the scientists who have been working on this in this area, and then they come out with what a concept of dislocation. So, if there is a crystalline defects of certain kind, then it can be shown that you need much lower stress for plastic deformation than what is expected from theoretical calculation. So, it is, if it is a perfect crystal, then that value is of course true, but if it is not a perfect crystal, if it is an imperfect crystal and the imperfections are of one kind and one what is called the dislocations. So, by introducing the concept of dislocations, one can realistically find out what is the actual stress required for plastic deformation. So, with this background, let us go back and see what is exactly a dislocation and why it needs a lower stress for deformation. Well, as per definition, dislocation is a boundary between a slipped and unslipped regions of a on a slip plane, regions of a slip plane, you can say also slip plane of a crystalline solid. Okay. So, a plane is deformed, and there is a partly it is deformed and partly is not deformed, or partly there is a movement of the atoms and on another part there is no movement of the atoms. So, that is the boundary. So, there will be a boundary, and the boundary, because it is on a plane, what we call the slip plane, because it is on a plane and the boundary becomes a line, it is an intersection of two different intersecting planes, and that becomes a line, and that is why dislocation is basically a line. The slip plane is a specific crystallographic plane of a crystal having much higher atomic density than the rest of the planes. Okay. Now, we will at this stage we will look back our concept of crystal structure and atomic arrangement to define what is a slip plane, and we have not discussed too much about the crystallography of atomic structures, but at this stage to understand the dislocation, let us try to look at little bit carefully what is a crystallographic plane and what is a slip plane. In fact, I am coming back to the basics of the crystal structure, atomic arrangement. These are the two structures which we have discussed earlier. One is so called the HCP structure, hexagonal close packed structure, and the FCC structure or face centered cubic structure. Both of them are close packed structures, that is the maximum packing what you can achieve with the solid spheres or the spheres atoms of the spherical nature. This is one can remember that this is actually what we call the AB packing, or this is A plane, this is B plane, and that is the again A plane. Whereas, in FCC this is A plane, this is B plane, this is C plane, and then again there is A plane. Now, if you can notice properly, you will find that the planes, we can consider the planes. Planes are nothing but an arrangement of atoms on an imaginary plane. Okay. So, these planes are always imaginary, and it is the atoms which are real. So, atoms, the way the atoms are arranged, you have some points here and we can draw some geometric pattern, and from that you can make some planes. You can imagine there are many different planes one can imagine from this diagram. For example, we have imagined a cube here, or we have imagined a hexagon, right. And so, hexagon has many different planes, some horizontal planes and also some vertical planes. So, this is a vertical plane, this is another vertical plane, and so on, whereas this plane is an horizontal plane. Okay. So, this plane contains some number of atoms. In this case, one can see 7 atoms are on the top plane, 7 atoms black ones are also on the bottom plane, and in between there are 3 atoms. 3 atoms forms a plane. So, there are horizontal planes, there are vertical planes, and one can imagine also inclined planes. Inclined at different angles. For example, here in cubic face center, you have the close packed planes are not actually horizontal planes. The horizontal planes is not the close packed planes. Here, for example, the top surface of the cube have only 5 atoms, and that they are not close packed arrangement. Close packed arrangement is a diagonal plane. The green ones is actually the close packed layer. So, it is a diagonal plane, and if you refer to this particular diagram, cubic arrangement, you will see this diagonal, and then this diagonal, if it is connected to this corner. So, you have this diagonal plane is actually the close packed plane. So, there will be another diagonal plane which is from this, the blue ones. The blue ones forms another diagonal plane. Okay. So, there are 2 parallel diagonal planes which are actually close packed planes, whereas the faces are not close packed. They close packed in the sense what is the atomic packing, how many number of atoms are there per unit area of that particular surface. That is what we call the atomic packing. So, in a close packed plane, the atomic packing is maximum. So, more number of atoms are there, and they are obviously their distance of separation will be the least, whereas in a open plane, open structure plane, the number of atoms will be less. So, the average distance of separation will be large. So, normally it is the close packed planes which are the slip planes, that means on which the atoms can move on that particular plane. One atom can go to the other atom, other atomic site or the other lattice site without much difficulty, because it has to travel a less distance to goes to the next equilibrium site. So, slip planes are defined actually as the closest packing planes, and depending on the structure they may be different, and there may be number of sets of slip plane in a particular crystal structure. Okay. For example, here in hexagonal structure, all the horizontal planes are slip planes, and horizontal planes are close packed planes, whereas the vertical ones are not the close packed ones. Vertical ones are open, and therefore, if the atom has to go to its next equilibrium site, for example, this one, it has to go to the next equilibrium site vertically, it has to move this much, whereas in the horizontal plane, if the atom has to go to the next equilibrium site, which is this one, so the distance of separation is much less. So, it is easier for the atoms to move on the close packed planes than on the open planes, on the other than close packed planes. So, that is the importance of slip plane when we are talking about the movement of the atoms. For that we need always to know what is the slip plane and which direction. There is not only the direction, not only the plane, but also we have a concept of close packed directions. So, in that along that direction, the distance of separation between the consecutive or between the neighboring atoms are the lowest, and so the distance to be traveled is also less. So, you need less energy for that movement of the atoms along that close packed direction or on the close packed plane. So, that is the concept of slip plane. So, there are many system of slip planes in many crystals depending on the crystal structure, what we have discussed earlier. We have different sets of close packed planes or which may have or close packed directions. We have also discussed that all structures are not close packed, there are open structures also. So, but they do have a slip plane, and that is why whatever the plane has the largest atomic density, that will be called the slip plane. Okay. It may not be fully close packed plane, but even in the open structure, the highest atomic density plane can be called as a slip plane, because that is the plane on which the minimum number of or minimum distance has to be travelled for the movement to take place. So, that is our concept of slip plane, and as you have discussed earlier or given the description. Now, coming back to the description of dislocation or definition of a dislocation. Dislocation is a boundary between slipped and unslipped regions. There will be always slipped and unslipped regions, because you are talking of deformation, and that slippage is taking place on the slip plane. So, this is we have discussed that the slip plane is a specific crystallographic plane on a crystal of a crystal having much higher atomic density than the rest of the planes. Okay. With this background, let us try to see what is actually a dislocation. Dislocation, because it is related to the deformation of the crystal. Okay. It is a plastic, also the plastic deformation. So, it is a permanent deformation where the dislocations are coming up. For the elastic deformation, where there is no permanent deformation, there is no question of dislocations to be formed, or dislocations are not needed. This concept of dislocation is irrelevant there, whereas only for the plastic deformation part, the concept of dislocation is very, very important. Now, let us see, this is a volume of a crystal, and these grid lines are actually the planes of the atoms. So, on those intersection of the grid lines there are atoms. These at each intersection, let us say there is an atom. Okay. So, we have a horizontal plane, a large number of horizontal planes, and then we have also a large number of vertical planes on which the atoms are residing. Now, in this let us see that we are trying to deform this crystal. Ideally what will happen, the way we have discussed earlier, here we are allowing or you are applying a stress on the top half of this crystal. We are allowing a stress in the right direction, in the forward direction, whereas in the bottom half we are allowing a stress in the backward or the from right to left. So, this is trying to slip in this direction and the top half is trying to slip in this direction. So, that is how we have applied the pressure. Normally, if there is no defect in this, what would happen? There will be a cooperative movement or simultaneously along this plane, along this middle plane, all the atoms above this plane will try to move in the right direction and all the atoms in the bottom of that plane will try to move in the left direction, towards left. Now, if we see that there is a cooperative movement of completely all of them are moving simultaneously, then we need a very higher stress. That is what the theoretical stress we calculated. So, if all the atoms on the plane are moving simultaneously, then you need a much higher stress. Instead, if you assume some kind of a different configuration, for example, like this, you see at this stage is an intermediate situation when there is no step has been formed here, all of them are still intact, the atomic positions have not changed here, okay. It remains more or less the same. It might be experiencing some stress, but it has not moved away. Whereas, on this side this atom which was here to start with, it has moved one interatomic distance. So, there is a movement of each of these atoms which was originally on this edge has moved one interatomic distance, whereas on the right side there is still no movement. So, there is a boundary, where the atoms has moved and rest of the atoms are still intact where it was originally situated. So, referring to the diagram once again, there is a boundary here. On this side you can see there is a little bit of deformation. This is one plane, this is which was a vertical plane, and because of this application of the stress, there has been a movement, there has been a shift of the atoms, and this on the right side there is no shift, but the left side all these atoms have been shifted one interatomic distance, and as a consequence of that there is one extra plane, which extra plane of atoms which is coming up, which is forming a kind of boundary, on the left part of it the atoms have been shifted or the deformation has taken place. On the right the atom no, there is no deformation, there is no deformation, and so there is a boundary between the slipped region on the left and the unslipped region on the right. So, that is what it refers to. So, this is an extra edge of plane, edge of atoms, which is called an extra plane, right. This has been compressed, the top part has been compressed, the right bottom part has not been compressed, right. There may be slight deformations because there is a elastic deformation, but there is no plastic deformation so far. If you go on pressing this, in fact, to start with, another thing we must discuss, to start with, at the very first step this dislocation would have been here, the extra edge would have been here, one step away, and as step by step movement is taking place, that extra edge is shifting from the left to the right, okay, slowly, and more deformation is taking place. So, coming back to the diagram, you will see after some time this particular extra edge will shift to the next point, and then to the next point and then to the next. And once that is done, and then it will go out, which means the whole of the top part has been shifted one atomic distance right to the right, and the left part to one atomic distance left. So far at this is a intermediate stage when there is no step has still been formed, but one step has been formed here, no step has still been formed. But after some time, if you continue to apply the stress, this extra edge will slowly move towards that and finally go out. So, there will be a step will form and it will come to an equilibrium side. That means, the stress will also be released inside, there will be no stress. As a result of that stress, a step physical deformation has taken place and a step has been formed. If you still continue to apply the stress, a more number of steps or the step distance will go out, will be increasing. So, finally, it may break. Okay. The whole of the top part will slip away from the bottom part, and one can say it has been cracked here. Okay. So, this part and this part has been separated away, but before that there is an intermediate step, there is a transition region when there is a partly slipped and partly not slipped, partly deformed and partly not deformed. So, this is what basically the concept of dislocation. So, the dislocation is actually the intersection of this plane, this extra plane here, and the slip plane. Okay. The slip plane is the horizontal plane here with the blue line, that is the slip plane on which the atoms are slipping, on which in the sense that is the intersection point where the top atoms are moving and the bottom atoms are residing at their own site, or there is a relative displacement basically. So, the dislocation is defined as a boundary. This is the boundary, on this diagram is actually the point. Okay. The line is on the towards depth, along the depth of this crystal. Okay. So, the line is away from us. So, that is the boundary, the boundary between the extra edge of plane and the slip plane, the horizontal plane. Not the dislocation is not the extra plane, it is the boundary of the extra plane or the junction of the extra plane along with the horizontal plane, that is the slip plane. So, again coming back to the definition, if you can go back to the definition, you say the dislocation is a boundary between a slipped and an unslipped regions of a slip plane of a crystalline solid, right. So, the slip plane, it is lying on the slip plane and it is a boundary between the slipped portion of the this is the slipped portion and right side the unslipped portion. So, that is how. So, the dislocation, the presence of dislocation has helped actually, presence of a dislocation has helped the movement of the atoms, movement of sliding down or sliding up and down, sliding up down rightwards or leftwards much easier at a much lower stress. So, this concept, it is not a cooperative movement of all the atoms on a slip plane simultaneously, but a step by step movement. So, one is moving to the other and then it is going to the next site. All of them are not moving in a cooperative way. If that has to happen, it would have taken a much larger stress for deformation. Okay. So, the movement of this defect, what is called a line defect or a dislocation, presence of a dislocation makes our life much easy or makes the material more plastic. Okay. It can be deformed at a lower stress. In fact, that is the advantage so far as the metals are concerned. Okay. Metals, so the toughness of the metals are very high, because it needs or it can accommodate lot of plastic deformation. This has its own advantages if you want to particularly for fabrication, use, everything. Okay. Whereas ceramics, that kind of deformation mechanism is not there, and therefore, it is plastic deformation is very negligible, and therefore, until unless it is a very high temperature, almost very close to its melting point. So, there of course, there may be some concept of dislocation will be important, but otherwise for ceramics the plastic deformation is not there. So, there is hardly any dislocation movement. In fact, this is the next step, another picture of the same thing. We are not having a isometric view, but it is only a section of the vertical plane, and one can see here this is the dislocation, the extra plane we are talking about. So, once you have an extra plane over here, this is the dislocation. So, again dislocation here is a point, it is extending perpendicular to the surface of the display unit. Okay. So, these are all dislocations here, this is another point. What it is shown here is as the dislocation is moving from left to right, okay, it is, as you can see, it is here, it has moved one distance or one interatomic distance, it has moved further, and finally, it has formed a step, okay, step on the other side. It has started with the step, it has not been shown here unfortunately. It has started on the step on this side, or if the dislocation is already there in the material, dislocation has not been created, but the dislocation, for example, for some reason it is already there in inside the structure, and if you apply stress like this, it will form, dislocation will move away from the interior of the material to the surface, and as soon as it comes to the surface, it forms a step. So, there is a deformation, and that is what it shows, surface step is formed when the dislocation is moving. So, the dislocation is not a stationary one, okay. Dislocation is moving for many, it can be moved or it can be mobile for many under different circumstances, particularly if you apply stress, it will start moving. If you apply temperature, increase the temperature, dislocation may also start moving, because for different reason, it is for the thermodynamic reason. Dislocation, because there is a stress field around the dislocation, because there is an extra atoms have been accommodated, which was not supposed to be there, and therefore, there is a internal stress generated, and that stress increases the internal energy of the system. So, if you apply temperature, there is an activation energy you are supplying. So, the stress like to be released. So, the dislocation starts moving, and as the dislocation go out of this crystal, the stress is released, okay, because it is at the expense of forming a step, at the expense of step in this sense, as actually it is forming a deformation, it is generating a deformation, it is resulting into a physical deformation. So, more and more physical deformation is taking place, dislocation density may be reduced. Okay. Well, with this there is another concept one is to remember, what is called the Burgers vector, okay, because there is a movement, so vector is important, it is in the particular direction. So, movement is taking place in a particular direction. So, there is a vector, atomic movements are taking place. So, if you have a extra edge of plane here, this is your dislocation, as you can see, this plane is slightly deformed, and finally, away from the dislocation, this is the dislocation point or dislocation line, and around that there is a lot of stress field, because the atoms are stressed back pushed back. So, there is enough of energy generated over there. there is a compressive stress here and there is a tensile stress here, because they have been at a larger distance, whether here it is at a shorter distance than the equilibrium distance. Anyway, so you have an extra edge on the extra plane of atoms on the top surface on the one side of the slip plane. The red one is the slip plane. Okay. So, there is an extra edge over there and extra plane, and here one less extra plane. So, the movement of atoms are like this. This atom would originally, this second atom was originally at the first side, and because of the application of stress it has moved to the second side. So, similarly this one was on this side and it has gone there, and the extra is there because the step is still not formed. So, once this slowly goes on the right and goes to the surface, it forms a step. So, there is a extra number of one extra number of planes. So, Burgers vector is this vector, that is the unit distance. The unit distance in the direction of the movement of the dislocation on the slip plane, of course, the movement of the what is the minimum distance of movement and which direction, that is what is the Burgers vector. So, and you can find out Burgers vector one simple way to identify what is Burgers vector. This you start from there where the step has been formed and then go around this dislocation equal number of atomic distances. Okay. If you go 1, 2, 3, 4, 5, 6, 7 and then you come to 7 on this side or less, but it has to cross this dislocation slip plane, you come down the slip plane and then again go in this direction same number of distances, and finally we will see that it has ended up here. So, you draw what is called the Burgers circuit around the dislocation point or the dislocation line in fact. So, you draw this Burgers vector, draw this Burgers circuit taking equal steps in all the 4 directions, and you will find there is a gap formed, and it has you have started with this point and you have ended up with this point, and then this distance becomes your Burgers vector. So, it is the unit, basically it is the unit distance of movement on the slip plane and in the direction of the movement of the dislocation, because that is the movement which has caused the formation of the dislocation. Okay. Now, dislocation as per definition is at the boundary of a slipped and unslipped region, and here we have seen there is a extra edge. Okay. Extra edge is formed here, extra plane which is the dislocation, and this particular dislocation, this is one variety of dislocation. There is a second variety of dislocation also, we will just discuss that. The second variety of dislocation is this is called the first one what we have discussed so far is called the edge dislocation. Okay. It is called the edge dislocation. It forms an edge along the slip plane, on the slip plane. Okay. Whereas, there is another variety, the same, it also forms a deformation of a similar nature, but the mechanism is slightly different. Mechanism is shown here in this picture. You can see this is once again the total crystal, and these grid lines are actually the atomic planes, both horizontal planes and the vertical planes. You have also applied a stress from the left to right. This is the direction, that means the top part is being tried to move in the right direction and the bottom part is being tried to move in the left direction, but there is slight difference between the earlier discussion or earlier diagram and this diagram. In the earlier diagram, the whole of the top part was being tried to push to the right, whereas here the stress has been applied in such a way that only the front portion is being tried to push in this direction, not the total not the total of the crystal. Okay. So, the back part here there is no stress. So, you are applying not an uniform stress across this plane, but you are applying a more intense stress on this portion, front portion of the crystal, whereas there is no stress on this portion. So, you are trying to distinguish between two regions, one is the stressed region here and the back side is still not stressed. Under such situation, what will happen? Once again there will be a boundary between slipped and unslipped portion. This portion has slipped, okay. This portion has slipped, whereas this portion has not slipped. So, the boundary is in a different direction now. So, the boundary is along the direction of application of the mechanical stress or shear stress. Earlier we have seen the boundary is perpendicular. Boundary is perpendicular to the direction of the slip or the direction of the application of slip, application of the stress. Okay. If you look back, this boundary is in the distance is in the perpendicular distance compared to the direction of the applied stress. So, the movement is taking place in this direction from left to right, and the dislocation boundary is from the front to the back. So, the dislocation line is perpendicular. Dislocation line is perpendicular to the application of the stress, whereas in the second case the dislocation line is parallel. Dislocation line is parallel to the direction of the application of stress. Okay. So, here you can see we are applying stress in this direction, the boundary is also along the same direction, because the unslipped portion in the back and the front portion is the slipped portion. So, this black part here is formation of a step, and here there also a step has corresponding step has already formed. So, this part is the slipped portion and unslipped portion is there, and the bottom is also unslipped. So, the distance, the boundary becomes in a different direction, and this is called screw dislocation. The previous one, the first one we have discussed, is called edge dislocation, and this is called a screw dislocation, right. And the basic relationship, well, there are two vectors, there are two important vectors associated with any dislocation. One is the unit vector along the tangent to the dislocation line or in the direction of the dislocation line, that means the slip direction along the direction. No, it is not the slip direction, it is actually the Burgess vector is the slip direction, and as a result of that slippage a line has been formed, and this is the tangent to that line. Okay. So, these two vectors are important, and in case of, I will come back to that. The relationship between the Burgess vector and the slip direction of dislocations are, in case of edge dislocation, the tangent vector is perpendicular to the B vector, the Burgess vector, whereas in the screw dislocation the tangent vector is parallel to the B vector. Okay. But the slip direction always in the direction of the Burgess vector, because the Burgess vector determines the direction of the slip, direction and magnitude of the slip also. It is basically an interatomic distance so far as the magnitude is concerned, but the direction can be at different directions depending on the application of the stress or what kind of stress field is generated there. So, these are the two vectors which are important so far as the dislocation is concerned. So, there are edge dislocation and then there are screw dislocations. Okay. However, these are the ideal cases, these are ideal situations where either the Burgers vector is parallel or perpendicular to the tangent vector, but in practice actually there will be a mixed vector, what is known as mixed vector, right. Oh, I am sorry. Yeah. So, these are the two dislocations, nature of dislocation. One is edge dislocation, it is represented by this symbol, two lines joining perpendicularly, because the B vector, the Burgers vector is perpendicular to the T vector, the line vector of the dislocation, whereas in the screw dislocation it is parallel and it is represented in the form of a circle, half circle, okay, or incomplete circle. Now, this there is an arrow there, okay, there is an arrow there. So, it is also represents a direction in which direction the screw is moving. However, we will come to that. In most cases they are not ideal situations. So, these lines are not either straight lines or whatever we have discussed so far, as if the dislocations are always straight lines. Actually, in practice dislocations are not never straight lines, it is completely curved lines, and therefore, these curved lines have some component of edge dislocation is there, rest of the components may be a screw dislocation. Okay. So, when we talk about a dislocation line, it is not always a perfect screw dislocation or a perfect edge dislocation. They may be composed of many combinations of edge and screw dislocations, and therefore, they becomes very curved lines. So, normally dislocations are of mixed character, partly edge and partly screw, and therefore, they are never straight lines, but complex curved lines. Okay. So, one can distinguish dislocation, one can see dislocations under electron microscope, under electron microscope, because they are stress fields, they generate stress fields around the dislocations, and dislocations are also associated with some amount of energy. I am not going to the details of that, but because of the energy, because of the stress field there, electron beams will be absorbed there. So, you have less of transparency. So, as a result you can distinguish between a dislocation line and what dislocation lines are not there. So, dislocation line do appear in an electron microscope in the form of a complex curves of different crisscrossed lines. Okay. So, that is the dislocation. We will see this is a example of a mixed dislocation. Instead of a straight line, we have a circle or elliptical line. So, this is the middle portion is a slipped region and this is unslipped region, or it may be vice versa depending on where the stress is. If the B vector is in this direction, then on this you have the slip direction is here, the dislocation line is in this direction, and you have the so called T joint or T symbol here, and this is reverse T. In fact, this is reverse T and this is actual T. So, the directions are different because the tangent to this line is different. Okay. The vector T vector is different, B vector is always in this direction, but T vector may be in this direction or in this direction or in this direction and in this direction. So, for these two, B vector is parallel to T vector, but in different directions. So, this is a clockwise rotation and this is an anti-clockwise rotation. So, that is also important how it can be denoted, and then here you have a reverse edge dislocation and a normal edge dislocation. So, these are ultimately this becomes your dislocation line. So, this is the boundary and this is the line what you see maybe under electron microscope. So, that is all for this time being, and we have some more discussion maybe in the next class we will discuss that. Thank you.